Okay, good afternoon, ladies and gentlemen. It is time for another session of Maths with Gary. And today I want to talk about a concept in computer science that we use to analyze algorithms for efficiency. It's incredibly important in modern computing to pick efficient algorithms to perform whatever it is that you're doing. And this could be sorting a sequence of some sort. It could be calculating the determinant of a matrix. It could be doing something pretty simple like searching a sequence or a list for a particular item. There are different ways of doing all of this, and some of them are better than others. So we're not going to talk about all the different ways of doing it and how to analyze that, but we are going to talk about the language and the notation that we use to describe them. So let me share my file. And I want to imagine for a moment that we're talking about the process of sorting a sequence of length n. And basically we've got to compare some stuff and we've got to swap some stuff around. Now there's a number of algorithms for doing this. One of them is called selection sort. And the way that this operates is to make a number of passes through the sequence. You choose the largest item, when you could choose the smallest depending on how you word the algorithm. So you then swap that item into its correct place and you make another pass over the remaining items that are not yet sorted. You don't go over the stuff that's just been sorted. You should consult a text on algorithms or a good discrete maths textbook, such as Discrete Maths by Richard Johnsonbaugh. Excellent text, highly recommend it. There are more comparisons than swaps. So we're just going to concentrate on the comparisons, but you could count them both if you. It's very hard to count them both because you don't know the actual order. And selection sort is not one of the better sorting methods because it doesn't take any advantage of any order that already exists in the data. So for example, you might have two items. This one in my right hand might be further along the sequence than this one. So we should try and keep them in their order. Selection sort won't do that, or it may not do that. So there are other sorting methods that are better, but we'll stick with selection sort. Not going to explain why, but the number of comparisons is given by f of n is equal to a half n squared plus a half n. Okay, if you sort using selection sort a sequence of length n, you will make a half n squared plus a half n comparisons. And we would like to compare this to other sorting methods and see which is the most efficient. Well, to do this, we focus on the fastest growing term in f of n, and we work on the principle that as n increases, this term is going to come to dominate. Because it grows faster than the other terms, it will overtake the others and become much more important. And if you look at the table and graph below for the difference, so we're going to be comparing a half n squared plus a half n and a half n squared. And if you look at this chart, and we go up to 512 items, the blue curve is exact. In other words, that's a half n squared plus a half n. And the dashed red curve is a half n squared. And at the scales of this chart, you cannot see any difference. Now, if we just zoomed right in on very early on in the graph, you would absolutely see a difference. But as n gets large-ish, and 500 items is not a very big list, imagine sorting the Beijing telephone book, for example. That would take a lot of comparisons. We're talking about a large number of people. So the term a half n squared describes the whole number of comparisons pretty accurately for large n. I've done a table here. I've got n in this column. I've got the exact term, which is a half n squared plus a half n. This is the single term, just a half n squared. And I've calculated the percentage difference in this last column. And you can see there is a difference. Yeah, there's still a difference, and the difference is actually getting bigger. But in percentage terms, it's actually getting smaller. And that's because the half n squared term grows so rapidly. This percentage difference is getting smaller and smaller and smaller all the time, even though the actual technical difference between these is getting bigger. It's like saying, what's more, $10 out of $50 or $10 out of $1,000? And the answer is that $10 out of $50 is a much bigger percentage. Yeah, so a half n squared grows much faster than a half n, and so it completely dominates the growth in the number of comparisons. And we're going to use that to simplify the growth, and we're just going to refer to it as being of order n squared. And what this does is it allows us to quickly and easily compare different methods. For example, a method whose growth is of order n cubed will generally be slower than a method whose order is of n squared. And the reason is that n cubed grows much faster than n squared. And so what we're actually counting or measuring is the amount of work needed to solve the problem. And so if the growth of the function is faster, that means it's having to do a lot more work, and therefore it's slower. And this is such a common thing to do that we actually need a new notation for it, which we call the theta notation or the theta notation. And that, of course, is a capital theta in Greek. So essentially, we're finding the fastest growing term, and we're using that to describe the growth of the function. And again, that growth of the function represents the amount of work done by the algorithm. So slower growing functions will actually represent more efficient algorithms, and faster growing algorithms, faster growing functions, I beg your pardon, will refer to less efficient algorithms. That should be the word functions right there. Okay, so it's sort of backwards a little bit. Bearing in mind that some problems are actually extremely difficult to solve, and they may not have an efficient algorithm at all. For example, the well-known traveling salesman problem is one of these, which just doesn't have an efficient algorithm. Yeah, it's not impossible that there will be one day, but I have my doubts. So here are our definitions. So the big O notation, if we've got constants C1 and N1 satisfying f of n is less than or equal to C1 g of n, as long as n is bigger than N1, then we say that f of n is big O of g of n. So f of n is allowed to be bigger than C1 g of n a few times near the beginning for small n, but eventually we've got to reach a stage where forever after, f of n is actually less than or equal to C1 g of n. And the big omega notation, if we've got C2 and N2, with f of n is greater than or equal to C2 g of n, as long as n is bigger than some finite value N2, then we say that f of n is big omega of g of n. And again, big omega is a capital Greek letter as well. That's a capital Omicron, which is one of the O's in the Greek alphabet. This is a capital Omega, which is the other O in the Greek alphabet. And if we've got both of those, then we've got a big theta notation. If f of n is big O of g of n and f of n is big omega of g of n, then we say it's big theta of g of n. So again, those inequalities don't have to be true for all n. There can be a finite number of values early on for which they're not true. This diagram will hopefully clarify it a little bit. So what we've got is the n axis here. Don't worry about the numbers, I've just completely made them up. So this solid curve is f of n. That is the actual growth of the function, which is measuring our algorithm in some sense. It might be the number of comparisons, it might be the number of swaps, it might be the number of multiplications. This top dashed line is C1 times g of n, and this bottom dashed line is C2 times g of n. And you can see f of n goes above that for a little bit, and then not quite, it might touch it, it might go below it. I think it just touches. but it's allowed to go outside of this envelope early on. But it's not very long before we find that f of n is always between, fingers crossed, because we haven't proved that, we're just relying on the graph to make it look like it's always going to be below, or between, sorry, always going to be between C1 g of n and C2 g of n. So that's what we mean. This top curve, it's below that, so it's big O of g of n, and it's above this bottom curve, so it's big omega of g of n. And if we've got both of those, it's big theta of g of n. And so there's a comment about what the upper and lower dashed lines tell us. Remember that f of n is the number of operations of whatever sort required by the algorithm, and that might be quite complicated. G of n is a simple expression that we're comparing it to. So we want something nice and easy that we can hang our hat on. In the example of selection sort, we had f of n was a half n squared plus a half n. G of n is just a half n squared. And that consists of the fastest growing term in f of n. Note that f of n equals big O of g of n provides what we call an upper bound on the growth of f of n. So f of n can grow no faster than g of n. And bear in mind, f of n may contain a constant multiplying g of n, but it still roughly describes the growth. F of n is big O of g of big omega, not big O, big omega. Mind your Greek letters, not your P's and Q's, mind your big O's and your big omegas today. So f of n must grow at least as fast as g of n. Bearing in mind there may be a constant multiple, complicating things slightly. And I've got a table here which shows the order of several functions with the fastest growing functions at the bottom. So the further you go down this table, the faster the functions grow, and any algorithm that is measured by these is going to work slower. Right? The faster the number of operations grows, because that's what this is counting. It's counting basically the amount of work your algorithm is doing. And so the more work it does, the slower it runs. So if you've got something that's measured by one of these functions near the top, that's great. If you've got something measured by these functions down the bottom, not good. So we've got log n, n log n, n squared, n cubed, n to the fourth would be below n cubed. Exponential functions like 2 to the n, 3 to the n, and so on come here. 3 to the n would be below 2 to the n. And the factorial function grows even faster than any of these up here. It's an extremely fast growing function. We can figure out some functions not appearing in the table by using the table. Which grows faster, n log n or n cubed? Well, n cubed is n squared times n. So we've got n squared log n and n squared times n. Which grows faster, the remaining n or the remaining log n? And of course, it's obviously the n term which grows faster. And so n cubed will grow faster than n squared log n. And so an operation that runs in n cubed time will actually be, an algorithm will be slower than an algorithm that operates in n squared log n. I want to look at some examples of how to find the notation. They'll be reasonably simple. Let's take f of n equals n squared plus 2n. The fastest growing term is n squared, so that's going to be my theta notation. So that's our g of n. N squared is our g of n. Okay, look at n squared plus 2n. I'm just going to replace the term 2n with the term 2n squared. And so we get f of n is now less than or equal to n squared plus 2n squared, because we've made this term at the back bigger, so it must now be bigger than f of n. In other words, f of n is less than or equal to it. And so f of n is big O of n squared, with C1 equals 3. And f of n is bigger than n squared because 2n is obviously a positive term. And so f of n is omega of n squared with C2 equals 1. Now, if you look back at our definition of big O and big omega, we didn't mention C1 and C2. We mentioned them, but we don't need to keep track of them. We don't actually need to know or quote the value of C1 or C2, but students find it very helpful to quote it. And I taught this subject for quite a long time, discrete maths it was called at the University of South Australia, or maths for computing. And students had terrible, terrible trouble because we'd go to all this work, we'd put in a lot of effort to find C1 and C2, and then they never appear. They disappear off the face of the earth. And everybody would know, where did they go? Well, we just don't need to know them. We need to know that they exist, but we do not need to know what they are. So, but I found that students understood it better if I actually quoted them. So I like to quote them. And so our f of n, and it would be really, really helpful here to say this, is that f of n is big O of n squared. Why didn't I say that? I should have said it. I did in the next one. F of n is 2n log n plus n. The fastest growing term here is 2n log n. And so we've got f of n is less than or equal to 2n log n plus 3n log n. And again, all I've done is I've replaced this slower growing term plus n with 2n log n. And so I've got f of n is less than or equal to 2n log n plus 3n log n, that's 5 log n. And so it's big O of n log n. Now C1 is there equal to 5, but we don't actually need to mention that. Doesn't hurt, but we don't need to. And if I drop the n term off, then the right-hand side is now smaller than f of n. In other words, f of n is bigger than 2n log n. And so f of n is equal to big omega of n log n with C2 equals 2. And since it's big O of n log n and it's big omega of n log n, we say it's theta of n log n. And as you can see, I should have actually done the same thing here because we've got big O of n squared and big omega of n squared. I actually should have said, look, it's big theta of n squared. And so that tells us that the growth is around about n squared. If you've got an algorithm that's, say, n log n, that's better, more efficient. And if you've got something that's, for example, 2 to the n, that's much worse. This one here, big theta of n log n, so it's growing around about n log n, and that tells us, that gives us a way of comparing different algorithms with different kinds of growth. Let's suppose that f of n is big O of g of n, where g of n is some function, and f of n is big omega of h of n, which is presumably a different function. We don't know its theta notation. It's got to be big O and big omega of the same function for us to give a theta notation. So if it's slower than g of n, but it's faster than h of n, I really don't know very much about it, if g and h are different. So I don't know whether it's really very, very close to g of n, or maybe it's really, really close to h of n. Maybe it's close to something different altogether. That doesn't tell me very much. Also note that the examples were rather carefully chosen. In particular, all of the terms were added together. So if I had, for example, f of n equals a half n squared minus a half n, I can't say that f of n is greater than or equal to a half n squared, and therefore it's big omega of n squared with C2 equals a half, because it's actually smaller. If I stop subtracting a positive number from a half n squared, I've actually made it bigger. So the omega notation, for example, is a little harder. It's definitely smaller than a half n squared, so the big O notation is easy, but the big omega notation is a bit harder. In this case, we would use our knowledge of functions, and so we'd say, look, if n is big enough, a half n is less than or equal to a quarter n squared for n above some small value, in this case n equals 3. And so we'd get f of n equals a half n squared minus a half n. That's greater than or equal to a half n squared minus a quarter n, which is a quarter n squared. And so it's still big omega of n squared. Hopefully you won't get too many like that, but that is how I would handle that. All right, ladies and gentlemen, I hope that this has helped you understand the theta notation and given you a handle on how to find it. So good luck with that. Keep doing maths. Have a great time, and see you next time. Okay, on that note, it's Gary out. I will stop sharing. All the best. Good luck with your study. Bye for now.